Welcome to the Deep Dive. This is where we stop chasing headlines and instead we take the detailed source material you've shared with us, the research papers, the technical reports, all that crucial field data, and we really distill what matters. We're giving you that shortcut to being instantly well-informed, and hopefully we'll give you some of those surprising facts that stick in your mind long after you're done listening. Today, we are definitely putting on our engineering hats. We're plunging into truly one of the most demanding environments on Earth for structural integrity. We're talking about the coastal zones of the Gulf Cooperation Council, the GCC region.
Right. And when we talk about building massive infrastructure there, we're talking ports, seawalls, bridges, huge high-rise foundations in places like Dammam or Dubai or Jeddah. You're not just fighting the heat. You are fighting the very chemistry of accelerated material decay.
And the core conflict here, the real enemy, is something called chloride diffusion, basically salt getting into the concrete. And it causes this rapid, devastating corrosion in the steel reinforcement. Our sources paint a really clear picture. This environment creates a perfect storm of factors.
A perfect storm is exactly the right phrase.
And it can turn a standard, 100-year concrete mix into a structural liability in less than 2 decades if you use those conventional standards.
And that's really our mission today. We're going to unpack precisely why those standard construction methods, the ones that work perfectly well in, say, North America or Northern Europe, fail so rapidly in the Gulf. We need to get into the technical drivers, understand the physics of that failure, and then look at the specific, highly engineered materials science solutions that are being used to fight back.
So essentially, we're figuring out how engineers are achieving these 100-year lifespans when the climate is trying its absolute best to destroy everything they built.
Instantly.
Yeah. Okay, so when we study structural failure in other parts of the world, you might be dealing with, 1 or 2 main environmental stressors, maybe freeze-thaw cycles, maybe some industrial chemical exposure.
Sure, a single dominant factor.
But the GCC is completely different. It's the stack-up of all these factors that creates that perfect storm we mentioned, where the effect is compounded, not just added together. So let's start with the most persistent, the most foundational threat, temperature.
Temperature is the silent, pervasive engine of decay here. And it is, without a doubt, the single greatest differentiator between the GCC and other global coastal environments. We are talking about sustained high ambient summer temperatures, frequently ranging from 35 all the way up to 50 degrees Celsius.
And that's not just a heat wave, that's the norm for months on end.
Exactly. And this high temperature doesn't just affect how the concrete cures when it's fresh. It fundamentally changes the long-term kinetics of chloride movement. The mechanism is governed by what's known as the Arrhenius relationship. And you don't need to get bogged down in the math. Just think of it as the governing principle of kinetic energy.
Okay, so kinetic energy. Diffusion needs the chloride ions to physically move, to jump from one point to the next within the concrete's pore structure.
Precisely.
So if you increase the thermal energy, turn up the heat, you're basically giving those chloride ions more energy, making them jump faster and more often.
You've got it. You're supplying the thermal energy needed to overcome what we call the activation energy, that internal barrier for the diffusion process to even happen. And because this relationship is exponential, not linear.
That's the key.
Exponential. That's the key. A relatively small rise in sustained temperature results in a drastically higher rate of movement. It's the difference between, say, tapping your foot and just sprinting toward the failure threshold.
So what's the quantifiable impact? When we compare standard operating temperatures, not extreme events, just the normal climate, what does that look like?
Okay, so if you take a moderate baseline environment of, say, 20 degrees Celsius.
Right, like we said, Northern Europe.
Perfect example. And you compare it to a typical Gulf summer average of 40 degrees Celsius, the effective diffusion coefficient, the D of that concrete, typically increases by 50 to 100%.
100%. So the structure is already aging twice as fast just because of the air temperature.
Twice as fast. And the real-world applications, the field data, it shows this acceleration is just relentless.
I can imagine.
When you take field samples and analyze them, identical concrete mixes, same recipe placed in the Saudi Eastern Province or the UAE marine zones, show a diffusion coefficient that's 2 to 3 times higher than that same mix would have in a cold climate.
The mix is the same, but the environment has just made it exponentially more vulnerable.
Exactly. And here's a critical detail that often gets missed. Mass concrete elements. We're talking large foundations, thick piers for bridges. They're like thermal sponges.
They hold the heat.
They hold the heat, they retain the heat generated during the early hydration process, and they just soak up the ambient heat of the summer. So this trapped heat ensures that accelerated diffusion just keeps going, often sustaining 40 or 50 degrees deep inside the concrete long after the air outside might have cooled down at night.
Okay, so we have heat acting as the accelerator, spinning that decay engine faster. Now we have to add the fuel, which is the chlorides themselves. The Arabian Gulf is, well, it's globally infamous for its salinity.
It is.
What makes the chloride concentration there so particularly aggressive?
It's largely a geological and a geographical problem. The Arabian Gulf is very shallow, and it's semi-enclosed. It has restricted water exchange with the open ocean, and you couple that with extremely high sustained evaporation rates.
So it's like a massive natural distillation process constantly concentrating the salt.
That's the perfect analogy. And the raw numbers, they're really telling. Arabian Gulf seawater, which is what's battering the coasts of the KSA Eastern Province in the UAE, ranges from 19,000 to 22,000 milligrams per liter of chlorides.
Wow. And how does that compare globally?
Well, the Red Sea around Jeddah and Neom is also very high, 18 to 19,000 milligrams per liter. That's comparable to the Atlantic Ocean reference, which is around 19,000. But the Gulf, the Arabian Gulf, often significantly surpasses that.
So we're starting with an incredibly high external concentration.
Right. And that high external concentration creates this massive pressure differential, which is the whole driving force behind Fick's law of diffusion. In the models, we call this the surface concentration, or CS.
So when that CS is so high, the structure is just perpetually under a massive attack.
Precisely. I mean, if your starting concentration is 30% higher than the global average, your material has a 30% harder job from day one, even if everything else is equal. The engineering defense has to start by acknowledging that high CS is a non-negotiable reality.
But the sources suggest that the sea itself might not even be the biggest threat for some of these elements, especially ones underground. We have to talk about the groundwater.
The groundwater. This threat is so insidious because it's often forgotten or underestimated in the design phase. In many of these GCC coastal areas, the water table is very shallow.
So foundations, basements.
Exactly. Foundations and basement structures are constantly submerged in the salt-laden groundwater, where the chloride levels frequently exceed 20,000 milligrams per liter.
Worse than the sea.
Potentially worse than the ocean itself. So think about the implications for critical infrastructure, like deep basement parking or subterranean utility corridors. These elements are continuously exposed to this huge driving force from below: foundations, buried podium slabs. The parts that are supposed to be the most protected and stable, they often become the first points of failure.
So we've got fast decay from heat, high concentration from salinity. The third crucial layer here is moisture, the constant wetness. High humidity along the Gulf Coast is almost universal.
It is, and it creates a very specific environmental condition that just actively promotes failure. Near the coast, the relative humidity, the RH, it routinely sits between 70 and 95%.
Wow.
And this keeps the concrete in a perpetually saturated or semi-saturated state.
Okay, and why is that constant saturation so critical to this decay mechanism?
Because chloride ingress happens through two main mechanisms. There's capillary absorption, or wicking, which is fast, but it only happens when the surface is dry. And then there's diffusion, which is slower, but it's continuous, and it requires a saturated medium to happen.
And in the Gulf, it's always saturated.
Pretty much. Chloride movement, specifically diffusion, only slows down significantly when the internal humidity of the concrete drops below about 75%. Given the coastal climate, where the RH is constantly above 70%, that necessary drying, it just rarely happens for any sustained period.
So the high humidity essentially switches off the concrete's natural protective drying mechanism. Diffusion, that slow, deep, continuous path, just rules the day.
That's it. If the concrete is always wet, the chloride ions simply keep diffusing inward, driven by that enormous concentration gradient we talked about. This is a primary reason why engineers in the GCC have to model chloride ingress predominantly using Fick's law for diffusion, not absorption models that might work in drier climates.
But then you have the splash zone, which just takes the severity to the absolute maximum. It's combining both mechanisms, right? Diffusion and capillary action.
It is the ultimate convergence point for failure. The splash zone, we're talking areas that experience tidal action, wave action, wind-driven spray, like the Jeddah Corniche or marine structures near Abu Dhabi. it undergoes these frequent, violent wetting-drying cycles.
Okay, so walk us through that cycle.
When the structure gets wet, the porosity of the concrete allows capillary absorption to rapidly wick chlorides a few millimeters inward. But then, when the wave recedes, the intense sun and wind cause the water to evaporate, leaving the salt behind.
Ah, so the salt gets left behind.
It does. And this isn't just drying. It causes salt crystallization within the pore structure, and it dramatically increases the surface chloride concentration, the CS, on the face of the concrete.
So with every single cycle, the surface salt concentration is being reinforced and increased, creating an even stronger driving pressure for the next wetting event.
Precisely. You get the worst of both worlds. Rapid penetration during the wetting phase, followed by an aggressive buildup of the driving force during the drying phase. This exposure is dramatically more severe than concrete that's permanently submerged, which is only subject to diffusion.
Right.
The GCC splash zone is, hands down, the fastest route to rebar corrosion.
Okay, we've set the stage. We have the environmental context,
Yeah.
heat, salinity, saturation. But for our listener, it's really important to grasp the technical magnitude of this temperature problem. We need to go from it's faster to, it's this much faster.
Right, let's put some numbers to it. When we talk about the Arrhenius effect on diffusion, we are talking about an exponential relationship. So think of the diffusion coefficient, dt, as the speed limit of the corrosion process. High temperatures essentially lift that speed limit without any warning.
So let's look at the data from the sources.
Okay, using standard industry parameters, a starting diffusion rate, and a typical activation energy of 35 kilojoules per mole, we can hold the quality of the concrete constant and just change the temperature, which is the one variable we can't control.
And let's not get lost in scientific notation. Let's just focus on the comparison, the ratio.
Good call. So, if we compare the predicted diffusion coefficient at a cold climate temperature, let's say 10 degrees Celsius, versus the average summer temperature in the GCC, 50 degrees Celsius, the difference in magnitude is just shocking.
And what is it?
The diffusion coefficient at 50 degrees is nearly 6 times higher than it is at 10 degrees.
6 times. That is the definition of exponential. It means that structure is consuming its service life 6 times faster just because of the ambient climate, totally independent of the mixed quality.
It confirms our central thesis here. The environment in the Gulf is intrinsically hostile to long-term concrete durability. Any model, any calculation that fails to accurately account for a sustained temperature input of 40 degrees or more is automatically underestimating the rate of failure by an enormous margin.
And that's why those conventional standards, the ones based on 20-degree modeling, are basically a guarantee of failure in the GCC.
Guarantee.
All right, so let's bring this down to the material itself. If we were to use a standard, off-the-shelf, ordinary Portland cement OPC, what does the data show is the baseline vulnerability, even before you factor in bad construction practices?
Well, regional performance data shows that standard OPC concrete, even when it's measured fairly early at 28 days, typically has an effective diffusion coefficient, a DF, that ranges from 2.0 to 5.0 times 10 to the minus 12 meters squared per second.
Which sounds tiny, but in durability terms.
In durability terms, that means a relatively open, porous structure. It's vulnerable.
And if we look at the construction side, where things can and do go wrong, how much worse can it get?
This is where the risk factor just jumps dramatically. If that OPC mix uses a high water to cement ratio, maybe it was specified wrong, or more likely it was watered down on site to make it easier to work with.
Right, for workability.
Or, and this is critical, if it suffers from poor curing practices, that DF can easily spike past 8.0 times 10 to the minus 12.
So what's happening there physically?
Remember, OPC needs careful hydration to build its strength and density. In high heat, water evaporates incredibly quickly. If you don't keep that concrete wet for the first 7 days, the cement paste won't fully hydrate. It leaves behind these large, interconnected capillary pores.
Express lanes for chlorides.
Exactly. They are express lanes for chlorides. A mix that was designed for a 5.0 coefficient quickly becomes an 8.0 material, and that guarantees the chloride threshold will be reached rapidly no matter how thick your cover is. This vulnerability makes OPC virtually unfit for purpose in these coastal zones.
Okay, so we've established the general failure mode: heat, salt, and wetness. But what's fascinating in the source material is how different coastal areas experience this problem. Let's talk about the regional variations, because Demum's challenge isn't exactly the same as Jeddah's, right? the dominant mechanism changes.
That's a great point. If we're ranking the severity of the GCC environments, the KSA Eastern Province, so the coastline from Dammam up through Jubail and Ras Al Khair, is consistently flagged as the most severe. It is the perfect convergence zone for all these factors.
And why? Why does that specific area earn that reputation?
Because it combines the three primary drivers we discussed at their absolute peak intensity. You have the highest regional salinity from the Arabian Gulf, up to 22,000 milligrams per liter. You have the highest sustained heat, 4 to 6 months above 40 degrees. And you have the highest persistent relative humidity, often hitting 95% right on the coast.
All three maxed out.
Maxed out. And on top of that, the local geology often features highly saline groundwater right below the surface, so the foundations are constantly submerged in aggressive conditions. When engineers model the service life here, the metric confirms it all. OPC structures hit that corrosion threshold at the steel depth in just 10 to 20 years.
10 to 20 years. That's catastrophic for major infrastructure.
It forces an immediate recognition that durability can't be an afterthought. It has to be engineered in from day one, or the entire investment is doomed.
So let's move west to the Red Sea coast, Jeddah, Yanbu, and those huge projects like Innoam. The salinity of the Red Sea is still extremely high, comparable to the Atlantic baseline. But the literature seems to highlight a shift in the dominant mechanism of attack there.
That's right. While the Red Sea itself is still very chloride-rich, around 18 to 19,000 milligrams per liter, the defining characteristic on the western province coast is the intensity of the wetting-drying cycle.
Okay.
It's often driven by different atmospheric patterns, higher average wind speeds compared to the more sheltered Gulf Coast. This just ratchets up the aggressiveness of the splash zones significantly.
So it's less about slow, steady diffusion and more about this constant, violent cycling.
It's the cycling that dominates. It's the constant washing, evaporation, and salt concentration that defines the exposure. And this focus on the cyclical exposure means that when you classify these zones according to international standards like ACI 318, the required exposure class is often XS2 or XS3,
Which are the highest levels of severity.
the designations reserved for severe or extremely severe marine environments. So engineers there have to be absolutely obsessive about concrete cover thickness and surface quality to survive that constant physical and chemical assault.
Okay, what about the UAE, Dubai, Abu Dhabi? They've seen some of the fastest, most expansive coastal development anywhere. What are the unique durability challenges that define that region?
The UAE faces these intense, localized problems. It's particularly driven by very high groundwater salinity, similar to the eastern province, and just the general issue of prolonged saturation from the long, hot season. The data shows very fast diffusion impacting foundations and underground parking structures, which are always in contact with those subsurface chlorides.
But the UAE also seems to stand out for its aggressive response.
It does, because of the sheer volume of high-value coastal infrastructure. I mean, the man-made islands, the massive port UAE specifications have been forced to adopt the highest performance targets as standard practice.
It's not optional.
It's not optional. They frequently mandate these specialized, non-negotiable concrete mixes, typically requiring 50 to 60% GGBFS replacement, paired with up to 10% silica fume, and all combined with a strictly low water-to-binder ratio of 0.40 or less.
So it sounds like the severity of the environment, plus the speed of development, has made high-performance concrete a regulatory default. It's not an upgrade. It's just the price of entry.
It's mandatory durability insurance. You have to buy it.
So for a crucial contrast, let's look at Oman, specifically its Arabian Sea coast. It's still a hot coastal environment, but the severity seems to drop off notably compared to the Gulf and the Red Sea.
It does.
What are the factors giving Oman that relative break?
There are three main reasons. First, the Arabian Sea has lower overall salinity compared to the semi-enclosed Gulf. Second, parts of Oman, particularly in the south, benefit from higher average rainfall and monsoon effects.
So it actually gets washed by fresh water.
It gets washed, and that provides surface washing and somewhat cooler temperatures, both of which mitigate the buildup of surface chlorides and slow down that Arrhenius effect.
And is this difference quantifiable?
Oh, absolutely. It's highly significant for the life of a structure. Engineering studies show that Typical diffusion coefficients in Omani coastal areas are 30 to 40% lower than what you'd measure in the KSA Eastern Province.
30 to 40%. That's a huge difference.
It's a huge difference, and while it's still a harsh environment, that substantial drop gives engineers a little more breathing room in their mix design. That 30 to 40% might equate to 20 or 30 extra years of service life for a comparable structure.
Okay, so we've established pretty clearly that the GCC environment is intrinsically designed to compromise structures, and to do it quickly. Now let's pivot to the engineering fight back. The solution, which is now the industry standard for any major project, lies overwhelmingly in these things called supplementary cementitious materials, or SCMs.
SCMs are the resilience layer. They are what makes a 100-year design life possible in this hostile environment. But what's truly fascinating, and maybe a bit counterintuitive, is the synergy between SCMs and the extreme GCC climate.
What do you mean by synergy?
Well, we noted that high heat and high humidity accelerate the failure of regular OPC concrete. But those exact same conditions actually benefit SCM performance.
How?
The high temperatures accelerate the pozzolanic reaction of the SCMs. This is a key chemical process that converts calcium hydroxide, which is a weaker byproduct of cement hydration, into calcium silicate hydrate gel, or CSH. That's the core durable component of concrete.
So the very heat that compromises OPC by causing rapid water loss is actually speeding up the chemistry that makes the structure more durable when SCMs are used. It's like a thermal assist.
It is a critical thermal assist, and what's more, that persistent high humidity ensures superior long-term curing. It prevents the early-age drying shrinkage that leads to microcracking. The end result is a more refined, denser pore structure that's achieved much faster than it would be in a temperate climate.
So SCMs are a must.
They dramatically decrease both permeability and the effective diffusion coefficient. Because of this, OPC mixes without significant SCM replacement are now considered highly vulnerable and are rarely acceptable for any major coastal infrastructure spec in the Gulf.
Okay, so let's break down the SCM hierarchy. What are the top performers, and what are their specific mechanisms for fighting chloride ingress? It's not just about adding some dust, right? It's a chemical and physical defense strategy.
Right. We rely primarily on two heavy hitters, and we often blend them for maximum synergy. First up is granulated blast furnace slag, or GGBFS. It's usually used as a high-volume replacement, anywhere from 50 to 70% of the cement material.
And what's GGBFS's primary defense mechanism against these chlorides?
GGBFS offers the highest chloride binding capability. This is a chemical defense. So when chlorides enter the concrete, GGBFS contains certain aluminate phases that chemically react with the free chloride ions and lock them up into harmless, stable chemical compounds.
So it takes them out of the fight.
It removes the chloride from the transport mechanism entirely. It's a game changer. Typical effective diffusion coefficients for these high-volume GGBFS mixes drop dramatically, down to values between 0.3 and 2.0 times 10 to the minus 12.
Which is a huge improvement over the OPC failure range.
Massive.
The second major player is silica fume, or SF, and that's more of a physical defense, right? It's all about density.
Absolutely. Silica fumes is an extremely fine material, and it's typically used in smaller dosages, usually 5 to 10%. Its strength lies in extreme pore refinement.
What does that mean, pore refinement?
The silica fume particles are so tiny they fill the microscopic voids and spaces within the cement paste. They break up the interconnected capillary channels that the chlorides use to migrate. It acts like a microscopic traffic jam, forcing the chlorides to take a much, much slower and more tortuous path to the steel.
But the sources also indicate that SF can make the concrete really difficult to place, especially in high heat. Is that trade-off worth it?
It is a significant practical trade-off, you're right. Silica fume increases the viscosity and the stickiness of the fresh concrete. It often demands more specialized admixtures and extremely precise on-site handling, which is a huge logistical challenge in 50-degree heat.
But the performance gain is worth it.
It's irreplaceable. SF mixes achieve the lowest overall diffusion values, sometimes dipping down to 0.2 to 1.2 times 10 to the minus 12, and that's why blending is so key. You pay GGBFS's superior chemical binding trapping the chlorides with silica fume's superior physical barrier slowing their arrival to create this dual-layered maximum security structure.
And we should probably mention the other SCMs briefly.
We should. Fly ash, or FA, is also used. It provides good long-term diffusion reduction at 25 to 35% replacement, though it's often a bit too slow reacting to be the primary solution in the Gulf's rapid construction timelines.
And there's a local one too.
Yes, locally, Saudi natural pozzolan, or SM pozzolan, performs really well in hot climates, especially where high humidity isn't guaranteed. It offers a reliable 20 to 35% diffusion reduction.
So let's move past the coefficients and look at real-world penetration rates. If you were building a bridge pier in Dammam today, what are the observed differences in performance between these mixes?
Okay, well, we have to start with the severity of the attack. Real project data confirms that engineers have to design for extremely high surface chloride concentrations, often measuring between 1.00 and 3.5% by weight of the concrete right at the surface. That is a relentless chemical assault.
Okay, so that's the baseline attack.
That's the baseline. Now let's look at penetration depth after 10 years of exposure. This is the clearest metric. In a standard OPC structure, after only a decade, the chloride front penetrates deep, often 25 to 45 millimeters.
And if you only had 50 millimeters of cover over your steel.
You are already halfway through your service life and flirting dangerously close to the rebar.
And what happens when we introduce these high-performance SCM blends?
The difference is just striking. GGBFS mixes at 50 to 60% replacement cut that penetration depth almost in half. They bring it down to 10 to 20 millimeters in 10 years. The chloride front is moving much, much slower.
So the concrete cover has years, even decades, more time to do its job.
Exactly. And when you incorporate silica fume, those penetration depths drop even further, down to the range of 5 to 15 millimeters after 10 years.
So what does this translate to in terms of service life? Because that's the ultimate payoff for the complexity and cost of these materials.
The service life reality is the entire reason for these stringent specifications. Without SCMs, reinforcement steel hits that chloride threshold and serious corrosion begins in a shocking 10 to 25 years.
Which is just not acceptable for public infrastructure.
Not at all. However, with the mandated SCM combinations, GGBFS plus silica fume, and a low water-to-binder ratio, the achievable real service life increases dramatically. We're pushing targets out to 80, 100, or even 120 years. This leap in durability is absolutely non-negotiable for supporting the long-term economic development goals in the GCC.
Okay, so achieving that 100-year lifespan requires not just a great mix design, but precision engineering and, critically, avoiding all those historical design and construction pitfalls. We should look at the common errors that designers make, especially when they're transplanting standards from temperate zones into the Gulf.
The source material is very explicit about 6 major pitfalls. First is a straightforward technical oversight. Modeling errors. It's the failure to account for that Arrhenius effect correctly.
They use the wrong temperature in the math.
They use the wrong temperature. Designers often use fixed law models based on a 20 degrees Celsius diffusion coefficient for their long-term prediction. But as we've established, that concrete is going to live at 40 or 50 degrees for much of its life. That one decision, the wrong temperature input, instantly invalidates the service life calculation. It can cut the predicted lifespan by 50 to 100%.
It's a simple but devastating input error.
Devastating. The second major error relates back to the severity of that constant salt bombardment.
Underestimating the surface concentration.
Correct. Underestimation of surface concentration, or CS. Designers often fail to account for the extremely high long-term CS that builds up, particularly in the splash and tidal zones. If you model using a standard global seawater value, but your structure is actually subject to a CS that's 50% higher because of evaporation, your prediction is going to fail. You have to model against the local, sustained, extreme concentration.
And the third challenge. This one feels like it's more about execution than design.
It is, and it's arguably the most heartbreaking one. Curing failure. We can design the perfect mix, a 0.35 water binder ratio with 60% SCMs, but if that concrete is not kept wet enough for long enough during that critical early hydration phase,
which is a huge challenge in 50-degree heat.
A massive challenge. If it's not cured properly, the effective diffusion coefficient, the DF, it just spikes dramatically. The material is fundamentally compromised right out of the formwork. It wastes the entire effort of that expensive, complex mix design.
I remember an anecdote about a high-spec project where they ran out of curing blankets on a hot day. The postmortem showed that even with a perfect mix, that single localized lapse raised the DF right back to near OPC levels in those exposed areas.
It shows you how the construction phase is often the weakest link. It's the point of greatest vulnerability. The next set of errors relates to what you might call environmental blind spots.
Well,
Designers sometimes fail to acknowledge that the high water vapor pressure and high humidity in the Gulf prevent drying. They might assume that since a structure is above the waterline, it's going to dry out, which would slow diffusion. But because the RH is so persistently high, diffusion just continues to dominate, making the structure far more vulnerable than they anticipated.
and the last one.
Finally, there's the tendency to underestimate the multi-mechanism ingress in the splash zones. It's not just simple diffusion, it's capillary wicking, and it's the physical force of salt crystallization all happening at the same time. Treating that zone as just marine exposure is fundamentally insufficient for durability design in the GCC.
So this all leads us to the new standard. What are the non-negotiable, stringent specifications that are now mandated for major GCC projects, the ones that are actually achieving these 100-year targets?
The requirements are now incredibly strict and they're performance-driven. These specs are mandated in massive facilities, from Dammam's ports to the complex waterside structures in Dubai and Doha. They focus on three main areas: chemistry, density, and physical protection.
So let's start with chemistry and density.
The most critical parameter is the water-to-binder ratio, or WB. The required minimum is less than or equal to 0.40, but the recommended value for maximum safety and durability in a severe environment is less than or equal to 0.38. This forces an extremely dense, impermeable paste.
And the SEMs have to dominate that mix.
Absolutely. The SCM content is a required minimum of 50% or more by mass, and specific combinations are usually mandated. GGBFS typically 50 to 65%, paired with silica fume in the 5 to 8% range. This blend ensures both that chemical binding and the physical pore refinement are maximized.
What about physical protection? The cover depth over the steel, that's the final sacrificial layer, isn't it?
It is the last line of defense, and in these environments, the cover requirements are significantly higher than global norms. Minimum cover is required to be between 50 and 75 millimeters, but the recommended value for a 100-year service life in a splash zone is 60 to 75 millimeters or more.
You're giving the chlorides a huge head start before they can even reach the steel.
It buys you decades of time. And finally, we have performance testing. Major projects don't just check the paperwork, they test the material's actual resistance. The Rapid Chloride Permeability Test, or RCPT, must yield very low charge values, 1,000 coulombs or less.
And they test the diffusion directly.
They do. They mandate a direct diffusion coefficient target, often written as D as SSM, of less than or equal to 2.0 times 10 to the minus 12. This combination of strict material inputs and verifiable performance targets is the only way to ensure these structures survive the Gulf's unparalleled severity.
This deep dive really shows the remarkable complexity of building long-term infrastructure in the GCC.
Right.
To synthesize the failure mechanism, you have the sustained, accelerating heat of the Arrhenius effect.
Right.
You have the extreme concentration of chlorides from both seawater and groundwater, and then the persistent saturation that ensures diffusion is always the dominant force.
Yeah.
This unique stack-up just ensures that standard OPC structures are going to fail rapidly.
But the great takeaway here is that engineering has developed a really robust counter-strategy. The solution lies in those supplementary cementitious materials, GBFS for the chemical binding, silica fume for the physical refinement, which dramatically lower that diffusion coefficient.
And crucially, the harsh climate itself provides a kind of thermal assist.
It does, accelerating the beneficial reaction of these SCMs and allowing engineers to confidently design structures that can last 100 years or more, despite all the environmental challenges.
It truly is a testament to material science adapting to and really mastering the forces of nature.
Indeed. And, we focus heavily on the mix design and the environmental forces. However, if you recall, one of the key challenges we listed was the devastating impact of construction practices.
Specifically, poor curing.
Exactly. The potential for poor curing to dramatically increase the effective diffusion coefficient, regardless of how good the mix on paper was.
That raises an important and I think a provocative question for you, the listener, to mull over.
Given the extreme logistical difficulty of controlling construction processes, of ensuring flawless curing across these vast sites in 50 degrees Celsius heat, how might construction methodologies themselves need to adapt?
Beyond just specifying a high-performance mix, to truly guarantee that 120-year service life, does the future of GCC durability lie in entirely new construction approaches? Maybe something like precast modules cured off-site in controlled environments, rather than just relying on better chemistry on-site.
Some food for thought on future resilience. Thank you for joining us for this deep dive into the demanding world of concrete durability.